All right, this is a video talking about the connection between quantum numbers and electron configurations. And what I'll try to explain to you is how if we took baby Einstein and locked him in a room, then he would predict the periodic table just from math equations, all right? And so what he's going to do is going to come up with these equations and solve for hydrogen and use that as the groundwork, and then think about like electron repulsions and give a perturbation that then he can apply to the different atoms, and then that will allow to explain how molecules are formed. All right. So the kind of connection with periodic table will come from the last chapter. I'm just trying to explain how he gets this math then to connect to be able to solve to get these deliverables. And so just going back, the easiest kind of equate relationship we learn in math is the linear relationship, y equals mx plus b. And why like that? I mean, it could be any form. We could get y plus a number equal 3 times x, and we rearrange it to put it in this form because that's the easy relationship. And what makes it easy is that once we have it in this form, we can simply plug in x and solve for y directly. And you know that kind of the main things is that we get it from a line, because it's the line nature, is that the slope and the intercept are the two things that describe that line. So we can have a negative slope or a positive slope and so on. The next level is a polynomial. And so we just get to the x squared, and of course you can go to higher order polynomials. And when we try and solve for that, again, we can plug in x and solve for y, just like the linear relationship. But what we start to think about are, what are the roots? Where does that cross zero is what that says. And in order to solve for this, then we use this quadratic equation that relates that a, b, and c, right? That's what that does. And it gives us the possibility. And from that, we get two solutions, plus and a minus form. And so in this relationship, Schrodinger's, what it's going to say is that these variables, A, B, and C, they have limitations on what they can be. And so what he says is that in the solutions, we only get to answer the roots here if that C is an integer and it goes from minus B to plus B. And B can only be an integer and it goes from 0 to A minus 1. And then the last one is A has to be a positive integer. It starts at 1 and just gets larger and larger. And so from that, then we can start to see the answers from the Schrodinger's. So if we start, then the lowest level will start at 1, and it means B has to be 0 and C has to be 0. And what's the next one? Is that A then is 2, and now we have options. B can be 0 or B can be 1. And whenever B is 1, we get more options. All right, and so that's going to be the kind of build up. We start with the lowest case and we start to build up from it. And so Schrodinger didn't use those labels A, B, C. He used N, L, and ML. Those are the three quantum numbers that comes from quantum mechanics. And what they're going to do is they're going to describe the electron. Where's the electron and the properties of the electron? And the first one is energy. And it ends up energy is only described by this N. And so what we get though is that when N equals 1, we get the low energy state, and we get N equal 2, N equal 3, and get these smaller and smaller jumps. And the crazy thing is this matched the observables for hydrogen, but it didn't match the other elements. And so in order to get it to that, what they have to say is that we can solve this fully with hydrogen. And if we do that and we put the other cases where L equals 0, we have S. And when L equals 1, we have P, and we get this answer. And this is the answer again for hydrogen, like how many states are available. And we get more and more states as we go. But when we have multi-electrons, then something magical happens. First is we start to get electron-electron repulsion. So the more of them we have, it's higher energy, and they go up accordingly. So when we put electrons together, they don't want to be together, so there's repulsion, so that's what pushes a higher energy. The second thing is we get our fourth quantum number, ms. And ms is going to be the spin moment of the electron. And we say it's plus a half or minus a half. And so what we're going to get then is way back when we started looking at the elements, and we said, we started with protons, right? We just add a proton. Every time we add a proton, we get a different element. And so we add protons, we add neutrons because they're the glue holding those together, those strong repulsions. And so if we just pick an atom, so we start with hydrogen here, and then so we can have an electron be like this, or we can have the 1s be like this, the opposite, spin up or spin down. So it can be plus a half or minus a half. If we then add a second electron and go to helium, what happens is, in this case, because this one is spin up, this one has to be spin down. Because this one is spin up already, this is spin down. So we get the same answer no matter what, all right? So this is for helium. If I add one more electron to go like lithium, again, I have the options. I can have it be spin up, or I can have it be spin down. So what is happening here is that lithium has 3 protons and 3 electrons. Is that this orbital diagram is showing what do the 3 electrons look like. And so it fully describes all the electrons. That's what this quantum mechanics is doing. All right. So they're not all the same. Like in the protons, there's a difference. And it ends up, it's these outermost electrons that give us the chemistry. That's why we have this kind of periodicity in the reactivity of them. Even though they're different elements and different number of protons, it's those outermost electrons that give us the similarity in the chemistry of it. So now we can start to see, if we go back and we look at hydrogen here, and we have the spin like this, the actual quantum numbers. So in hydrogen, N equals 1, so L has to be 0, ML has to be 0. And if we did it spin up, it would be plus a half. All right. So, or we can write minus a half. Either one of them are acceptable. And once we get to, let's just ignore this one and we'll go with the spin up and say that's it. Now when we add that second electron and we're going to put it like this for, like we did over there, that means the second electron has the other one, the other spin. And so each electron has 4 different quantum numbers. This is the meaning of the Pauli exclusion principle. And so again, going like we saw before, we can put this one. And so the quantum numbers would be 2 now. It's on the second level. It's still in an S, so it's still 0. And so ML has to be 0. And again, it's spin up, so plus a half. So this is the best descriptor, right? But it takes up the most space. So we have a condensed view where we write the same thing like this. And we often, the easiest way is just to say we have a 1s orbital with 2 electrons. That's what this is saying, and this is saying. So they're all the same thing, all right? And so for lithium, we would have 1s2, 2s1, all right? That's the electron configuration. We can show it with quantum numbers. We can show it with the orbital diagram, the full one or the compressed, or most of the time we use electron configuration. That's the connection between electron configuration and those quantum numbers. All right. So, all right. So now let's jump down and let's look at something like fluorine down here. And so if we wanted to look at fluorine, then how many electrons? It's using the full one, I would start here, 1s2, 2s2, and then you put the first one in, and then following Hund's rule, it says the next ones, we want to maximize the spin alignment, all right? So the first 3 in the P would look like this, and then the next ones then would be paired up like this, all right? And we would have 1 unpaired electron. So in the compressed view, it would look something like this. And in the electron configuration, there's 2 electrons here, so 1s2. And then there's, again, 2 electrons in the 2s orbital, 2s2. And now there's going to be 5 and 2p5. All right. So those are the easiest. The hardest ones then are going to be the quantum numbers. And so they always take the same form. Remember, this is telling us the same thing as these labels here. It's just a little more abstract. So plus a half, minus a half. And then we're going to be on the second level. And so 2, 2. So we have the S with 2 electrons in there. So plus a half and minus a half. And now that that's full, we're adding those electrons into the P. So the L is equal to 1. So 2, 1, 1. And so ML, then just to keep it kind of in order, 0, minus 1, 0, plus 1. And again, I did it with spin up. So I'm just going to keep the same, plus a half, plus a half, plus a half. And then afterwards, what I do, I started doing the spin alignment. And so again is 2, 2, and 1, 1. But now the difference is minus 1 and 0, that this was the opposite spin. So minus a half. So hopefully all that makes sense, right? Start with the easiest one and then move on. Sometimes people can do this, seeing this off the periodic table, and then kind of come over to the orbital diagram and then the energy orbital diagram, and then lastly the quantum number. But hopefully you can connect all the electrons. Remember, so what we're doing is we're describing fluorine has how many electrons, all those electrons. We're explaining where each of those electrons are. That's what's happening here. So now, so just be able to discuss quantum mechanics, how it explains the arrangement of the electron in an atom. And remember, this happens because we have those 4 quantum numbers. 3 comes from Schrodinger. You don't need that. Just know that there's 4, and they're going to be N is the principal quantum number, and it's going to relate how the energy is, and then L, because remember in the hydrogen, L doesn't matter. It's only N. But then when we start having multi-electrons, that's where that deviation comes from. So N and L combine to kind of dictate that relative energy. And then we can fill it up following Aufbau principle, Hund's rule, and the Pauli exclusion. All right. So hopefully all that makes sense. Let me know if you have any questions.